So let's start with our project layout. We have a very layered approach, as you can see, and each of the layers have their own responsibilities, and as far as possible, we try to keep the responsibilities non-overlapping, so it is more decoupled and it's easier to change and to maintain. So right at the bottom of our project stack, we have a library called CRUST, which is our IP networking library, and it has very useful features for the safe network, such as authenticated communication, and it anonymizes the communication so that it fits into the goal of our safe network. And on top of CRUST, we have the overlay network of routing, which is the DHT layer. And routing, as you know, is segmented, like the routing network itself has sections. It has disjoint sections, and that's the brain of entire mate safe. So it decides who to connect to, who not to connect to, and does what it says, routing. And on top of routing, you have the consumers of routing. So there are two consumers, as you can see. One is the vault, and the other part is the safe client libs. It's like a group of libraries, but you can consider them the client side. Right. Yeah. Okay. Yeah. Yeah. The safe client libs are the client side, so they expose facilities for the app developers to use to basically interact with the safe network, to build apps for the safe network. So how they do it probably ties into your previous question. It exposes a C layer, so C being the kind of a lingua franca, is the least common denominator. So most of the languages will have some kind of a C interaction, or they will provide facility to integrate to C. So users can use any language of their choice to develop their apps. But we do provide specialized features for Java and C# and Node.js, because we build apps based on those languages. But you can support Python and TCL and probably CMake, as Fraser would say. Then on the other side, you have vaults. So if you have clients, then clients will obviously store data in the network. So to store data in the network, you have vaults. They sit on top of routing, so they provide storage and access and do all the security features, such as if I have a data which is owned by me, then obviously nobody else who I have not given permission to can mutate the data or do something with it. They might get it. Gets are always free in safe network, but it might be encrypted, so it might not be of much use to you. But you certainly cannot mutate a data which is owned by somebody else. Okay, which direction was this? Right, so let's dive into more details about each of these. So the first one is, of course, CRUST. These are the requirements of Alpha 3, which is extending protocol support, improving user reachability, network simulation, encrypted communication. So we'll dive into the depths of each of these in more details, but there's just like a glossary, a laundry list. At this point, I would also like to mention that there has been a key change in CRUST. It stands for Communications in Rust, by the way, so it's a good name. So, so one of the key changes is that it has a major design overhaul. So it used pure MIO, and now it's completely ported over to Tokyo and Futures. And Populous and Andrew have done a wonderful job in doing that. So that has made it more modular. It has made it better in the sense it abstracts details of the state machine, so you don't have to handle them yourselves. So that's handled by the Tokyo and Futures crate. So it improves maintainability that way. Okay. Right, so the first point was extending protocol support, right? So if you know Alpha 2 right now runs on TCP. So what's the problem with TCP? Well, TCP is great if you have a public-facing endpoint, in which case it's the default thing that you go for a client-server model, right? So if you have a public-facing endpoint, you get a TCP connection, and then it gives you reliability, and it gives you congestion control, all those things for free. But the very fact that it gives you reliability and congestion control and all those things means that there is a request response, there is some kind of an acknowledgement, which is built into the protocol layer itself, into the transport protocol layer itself. And since that is into the protocol, all the routers recognize it. And since routers recognize it, and because of those bells and whistles that TCP has, it is more difficult to forge a connection when you don't have a public-facing IP, because routers are finicky. So if you have like peers behind NAT, so if you have peer A behind NAT and peer B behind NAT, and if they want to connect to each other, which will be the majority of the use cases, I guess, in the safe network, because you don't want to have a public-facing IP all the time due to security reasons, then TCP is not great. It still does hole punching and NAT reversal, but not as great as some other protocol. So we have to turn to some other protocol, and then we turn to UDP because it's equally famous. So UDP then complements TCP because it's simpler, lighter weighted, and because it doesn't have like reliability and congestion control and all that stuff. So it's easier to forge NAT connection with UDP. And it's a widely used protocol as well, as you can see in VoIP, in gaming, and a lot of other projects, like especially in cases where you have to fire and forget, you'll use UDP, right? So because you don't care about acknowledgements and all that stuff. But as with everything in life, when something has advantages in certain circumstances, it'll have disadvantages in certain other circumstances. So the disadvantages that UDP has is it's not reliable, right? So it's great for VoIP because the other end of message construction involves a human, most of who are intelligent, so are blessed with the ability to interpolate and extrapolate. So even if you don't understand, say, like 20% of what I'm saying, you can still reconstruct it and probably get the context. But not so much for the machines, right? They require a very faithful reproduction of, or a reconstruction of the entire message down to the last bit. Otherwise, it's sort of mutilated data or something like that. So in that case, UDP, since it lacks reliability, you can build in like forward error corrections and other things, but then that is a separate complexity on top of UDP. So instead of going for like forward error corrections, you get reliability usually out there in the world by the process of retransmission. And that layer is UTP, which is micro-TP actually, is the micro transport protocol. So that's the protocol that's used by the BitTorrent guys. So they have coded this libUTP crate in C, and but we don't have a Rust equivalent, which is asynchronous. So we had Carl Lurz. We asked Carl Lurz, as you might know that name. It's pretty famous in Rust. It's like the go-to guy for networking. So he coded this in Rust, and now we have a UTP crate in Rust, which we will use to wrap our UDP. So it not only helps us now, but it also helps like people out there in the open source community because, well, it's a crate that anyone can use. One wants the facilities of reliability and congestion control on top of UTP. Second thing, of course, is UDP is very bandwidth hogging. So if you have like a huge amount of data that you want to publish to the network, then it will probably choke the entire bandwidth. It doesn't play well with multiplexing with other applications and processes. UTP, on the other hand, the micro transport protocol, is pretty intelligent that way. So it plays well with other processes sharing the same bandwidth and adds like reliability and congestion control, all those things. I hope I go in the right direction this time. Okay, so fine. Now we have UDP and we have TCP. So what do we do with it? As I said, like the main problem is when you don't have a public-facing IP. So in that case, you have peers who are behind NATs, and then you have to implement one of the NAT reversal processes. So the simplest of it is you just go to the router manually, and then you port forward it, right? And then you have a public-facing IP. So you don't have to do anything apart from that. But routers also recognize this protocol called Internet Gateway Device Protocol, IGD, which, with the help of which you can actually programmatically talk to the routers and ask it to forward your ports and stuff. So we can do it via program. So that's one of the simplest ways to get public-facing IP. And once you have a public-facing IP, then everyone can connect to you and so on and so forth. But for that, you need to have a feature in router called UPnP, which is enabled. And a lot of routers don't have it enabled by default. So you need to go and enable it. And there's a good reason for it because it is dangerous. And it sort of gives the benefit of having a NAT, right? If you just go and forward your port, you might as well have a static public IP. So we need other mechanisms in case the users say like, nah, we are not comfortable with UPnP. It's a convenient feature, but if we are not comfortable with it, then of course we need other features. So the way we do NAT traversal is predominantly by hole punching, and that is where P2P crate comes into play. So this is one of the open source crates again for everyone to use out there and suggest corrections and contribute. So what it does is, so to actually appreciate a bit about P2P crate and this hole punching and NAT traversal, I need to go a little bit technical. Hopefully I'll give an example to make it interesting. But if you guys have further questions, you can always ask in the Q&A if I do get to that stage. So, imagine like, there are two things that router does, right? What it does is like it does mapping and it does something that's called filtering. So they are like hand in hand, they go hand in hand. So imagine like this thing is a router and I'm the local endpoint behind it and I want to talk to Viv, who always is very keen on talking with me. So you can see from his reaction. So what this router will do is, so the mapping part is how it will project me to the external world. So it will project me as, say, Spandan to Viv. So, and when Viv sees me, because he needs to know like who is communicating with him, so he'll see me as like Spandan, okay. And then what it also will do is, it knows that I'm talking to Viv, so it will update its filtering to say that, okay, Spandan wants to communicate to Viv, so in order to have a full duplex communication, I should allow everything that Viv also tells Spandan. So it updates its filtering to say that. And then I changed my mind. I said, no, I don't want to talk to Viv anymore. I want to talk to Josh. So now the router decides that, okay, what do I project Spandan as to Josh? In something called endpoint independent mapping, it will still continue to project me as Spandan, so Josh also sees me as Spandan. But it has updated its filtering to say that Spandan is no longer communicating to Viv, he's communicating to Josh, so probably I should not allow any more packets to come from Viv. So now I've started communicating with Josh, and if Viv sends any more packets, or if there are packets in flight, it's not going to reach me. If it does reach me, then that is good, then our job is simple, then it's the simplest case of NAT restriction. It's like the least restrictive NAT. In that case, we call it a full cone NAT. So that's the best case, right? So I can have a single socket which can talk to Josh, which can talk to Viv, which can talk to anybody out there, and everybody can talk back to me. And on the most restrictive side, you have something called port restricted NAT, which has updated its filtering to say that no, he can only talk to one person at a time. And this is where NAT traversal comes into play. And then there is something which is even more restrictive, which is endpoint dependent mapping, in which case I'll be projected as somebody else to, depending on who I'm talking to. So when I'm connecting to Viv, maybe I'm projected as, I don't know, XYZ. And when I'm talking to Josh, I'm projected as ABC. So they see me as differently. So that poses its own challenge. So P2P crate sort of recognizes most of these cases. It recognizes probably all the cases, and it tries to forge connections for most of these cases, and successfully. So it's a wonderful library, and you should see and try to use it. And a lot of brain work has gone into creating that one. But if you have a wonderful library, you need to test it in order to say that it's robust and all that stuff. The problem with it is, as I said, these have technical names out there in the wild, right? So endpoint dependent mapping, but endpoint independent filtering is sort of a symmetric NAP. Endpoint independent mapping is, and then endpoint independent filtering is full cone NAT, and in endpoint dependent filtering is port restricted NAT. So these are all various kinds of NATs, right? The problem is like each router has some firewall or some NAT. So in order to test like all these cases, you need to procure so many routers, which is difficult and not a very scalable solution because you need to get so many hardwares. So what we ended up doing was creating a library to precisely simulate the various behaviors of the routers, which is our NetSim crate. So this is what Andrew coded, and it's a very cool library. So what it does is, it's currently being maintained by both Andrew and Populous. So what this does is, it simulates various kinds of NATs. So you can say that I want to test a connection between symmetric NAT and a port-restricted NAT. And then I can introduce some random packet losses and real-world latencies, just to see, because latency is very important, because in all cases of hole punching, router sort of tends to remember like how long back was the connection, and if it is not working for a very long time, then it might close the hole, and then you no longer have the communication channel, right? So you need to simulate like if there is a latency and then the hole in the router gets closed, then what happens next? Like, do you forge another connection, or what do you do to keep it alive? You send packets and all that stuff. So it will let you test the complete robustness of the P2P crate. And it is a containerized testing, which basically means like you can have separate threads, and each of the thread represents your peer, which is behind a specific kind of a NAT, and then connect to each other and see whether it works out there in the wild. So pretty cool. Okay, that was CRUST from, I don't know, 10,000 feet view. Now we come to routing from 1,000,000 feet view. So already covered by, I guess, like David and Viv. So it's the trickiest thing to get right because of the problems of eventual consistency, and as it has been explained why so. But there have been quite a few proposals recently, including section graph and data chains, as was explained previously. Like section graphs are more ordered because it contains the hash of the previous and the hash of the previous and so on. So you can improve right up to the network genesis. So if there's a new node and you give it the section graph, then it can prove that, okay, this section is genuine because I do at least recognize the network genesis. So I trust this section and so on and so forth. And then data chains is a variation, or a section graph is a variation of data chains. And data chains was like a more loose ordering, right? So it allows for some degree of freedom. You will eventually have all those same events in both the chains, but in data chains, the order of the events might not be exactly the same as in section graph. In section graph, all the nodes have exactly the same order. Data chains, it's not so. But they will be consistent with each other. And right now, our routing team has been split into two. So one team is working on integration of yet another consensus algorithm, and one team is designing one very actively, and the approach looks very promising. And once we have that fleshed out, we'll probably put it out to the community. The reason why you see like routing progress is not like a smooth curve is because it is R&D, and it's very difficult to quantify R&D, and we do not actually want to put out something which is half-baked. So only once we have fleshed out to a certain degree of confidence, then we put it out. So you will see growth in spurts or progress in spurts. Like suddenly something will come out and that'll solve a huge number of problems and so on and so forth. So, and we have added some more firepower to the routing team recently. So introduction of Connor, introduction of Pierre, and the veterans and the likes of Fraser, G, Bart. So all those guys are working pretty much very hard in routing, trying to devise a consensus algorithm. The tricky part is the ordered consensus, which is also asynchronous, right? So you want an asynchronous consensus algorithm, but the order of consensus should be same. That would solve the problems of eventual consistency much better than anything else. Then you have node aging and secure message relay. I guess these two things are pretty much covered, but I'd like to give a shout out to some of the guys who were involved in the simulation of node aging and the relocation process. So of course we had our simulators, but it was extremely studied, verified, and probably even improved by Mav from community, TFA, and Neo, Rob. There are a lot of people. So all those guys, thanks a lot. It means a lot, of course. Makes us happy that somebody who's paying attention to our code. Makes us a bit nervous, to be honest. Right. Safe client libs. I'll very briefly talk about this because I don't want to steal Nikita's thunder. He has been doing a wonderful, wonderful job in safe client libs, managing it and managing people working on it and also coding a lot in it. So the paradigm shift is represented by the slide. So you have launcher, and previously it used to be a funnel. So all the apps used to go through the launcher to the network, but as we've said, it's not very scalable for mobile, plus it's not a great paradigm because you needed the launcher to be on all the time. And then in the mobile, you have processes that become backgrounded and then killed, and then there's apps suddenly don't have access to the network. So you have something called authenticator, which allows for, God, difficult to hear my horrible voice. It allows for the clients to be independent client engines and then communicate with the network. And once authenticator has authenticated those clients, they no longer require the presence of authenticator in order to communicate with the network. So it just requires, so because authenticator works in tandem with the vault, so it will go to the vaults and say like, okay, this and so made manager, this is the owner, and the owner has allowed such and such app, which is represented by a key, to access the network on behalf of the user, so please allow. And then the authenticator can take the back seat, in which case the clients can go to the made manager, and the made manager knows, okay, this is allowed, and it will charge the owner's account and allow the app to access the network. And then you have fine-grained controls in data managers, which I guess Nikita will talk about more. Programmable tag types. Okay, so what are these? So far, if there is a request that goes to the vault, this might be a little interesting because so far the request that goes to the vault, vaults always analyze it and apply certain rules to it in a very specific way. What this will allow is it will allow the user to say that don't treat my request or my data according to your set of rules, but here is the subset that please apply to the next request that comes to you. So it is the user who is specifying what rules are to be applied to either the data or the request. So, and those rules can be stored separately to the data or separately to the request, of course, and can be updated independently. So it might happen, so just as an example, one of the use cases is like, you can say which made account to charge. So if your account packet over there has a programmable tag type, it might have a field called, so this is not fleshed out, right? So this is just like brain dump. So you might have a field called applicable rules, which has a pointer to a mutable data, which contains the actual rules. So that's kept somewhere completely different in the network, some completely different place in the network. So when the request comes to the made managers, it will say, okay, what kind of account packet it is. And so, okay, it has a programmable tag type. So probably I'll just hang fire for now and look at the applicable rules. It'll ask the data manager to give it the mutable data that it is pointed to. And in that data, one of the rules might be, don't charge this made account. And instead of that, charge some other made account. So then this made manager will go and say like, okay, so I'll contact the other made account and ask it to reserve some balance. And if the sufficient balance exists and it is reserved, then you might get a response and then the request is forwarded. When you get a final success, it will again go to the other made manager and say, okay, whatever you reserved, deducted. So, and then you come back and then the user gets the response, the success response. So basically, that's one of the use cases, right? So you can have many, many, many use cases because it's a pretty strong concept. It's a pretty nice variation because it allows for flexibility. And also you can update the rules in real time. What that means is the very next request, which might be very similar to the previous request, will get evaluated completely differently because now the rules have changed. And hence programmable type tags can also be called like dynamic type tags because they allow for real-time updation of rules that are to be applied to the data or to the request going through made managers or maybe data managers in the future. Okay, that's the end of presentation.